So I'm now going to kind of, this is going to be the second video, so this is Bizarro Part 2. And what I'm going to do is I'm going to just kind of talk about some of the ingredients that's involved. So what Katz did is he kind of showed this thing for y to the p minus y is equal to x to the d. So d is going to be a certain polynomial of a certain degree d. This has lots of symmetries. And what you're going to do is we're going to use the symmetries to do this. So we're going to use the symmetries to decompose the cohomology. Okay, so let's do a quick review of the cohomology. So if x is a smooth projective, and we'll say it's geometrically connected, then what we're going to do is we have this zeta function that allows us to do the FQ points here. So this is the sum here, number of x q to the n, like so, and so there's the Grothendieck-Dwork theorem, which tells us that this is the product up to the 2 times the dimension of x, and let's say the dimension of x is equal to m in this video, of pi t negative 1 to the I plus 1. And so this thing just looks like a product of p, the odd things in the top of polynomials, like so. And we know, okay, that these pi's, they have integer coefficients, and we can write them here as a product. So we have this degree up to the pith degree of j is equal to 1 of 1 minus alpha I j t, like so. We read it like this. So it turns out that these alpha ij's are algebraic integers. I'm not sure who did this. I think this is to do, well, I'll say who it is over here after I look it up. Then it turns out that here that these alpha ij's, since we're over q, we're going to take the usual norm, and this thing is going to be the square root of q to the ith power. So if you're on ith cohomology, you're going to have the ith power here, and so this part is due to Lin, and this is the Riemann hypothesis for varieties over finite fields. Also, we know that P0 is going to be, P0 of t is just 1 minus t, t here, and that the top one of t is just equal to 1 minus q to the n of t. So we kind of know a little bit about the structure of these things. Well, also we know where these things come from. So there's this cohomological interpretation. The cohomological interpretation says that here we have this crystalline, so we can define the crystalline cohomology, which is this inverse limit of, well, we take this crystalline thing here, Wn of Fq, so we take these truncated p-typical width vectors here, or we could take this L-adic cohomology here. They're both Weil cohomology theories. I have an introductory video on this. So this is when we take the atoll site instead of the crystalline site, and then we have to go to the algebraic closure here, and we take the inverse limit of these things here. so here L is a prime not equal to P is a distinct prime. And then in both of these cases, we have the Frobenius acting. So, and it'll turn out that that in this case, the ith polynomial that we gave in the previous page will be the determinant of 1 minus Tf acting on hi L of x tensor with so QL. So this is the L-adic. Or it'll be the determinant, they're both the same, 1 minus Tf of hi, the crystalline, of x, tensor with k. Here k is going to be the fraction field of the Witt vectors, the full Witt vectors, p-typical Witt vectors here. And the way that these are related to the rationality of the thing is that we had there's this Lefschetz formula, q to the n is equal to the sum for I greater than or equal to 0, negative 1 to the I of trace of the Frobenius acting on cohomology. So we plug this thing f to the n here. So we have this. So this is this part, okay, and so this is for n greater than or equal to 1. Okay, and so using the logarithmic derivative together with this, where is it? The formula here. Where is it for the? Did I not write it down? Oh, I did write it down. Using a logarithmic derivative and plugging this in here, we get this thing. Okay, so I'm at 6 minutes. I'm trying to not go over 10 minutes. And so let me just say that all the eigenvalues. So given this data, so okay, so I want to rehash what these facts are. So these facts here. Okay, so given what we said, the bullet points, so it turns out that, let's actually do this. We'll call these things here dagger. Okay, so dagger plus the what this Grothendieck and Deligne imply, or maybe are equivalent to, all the eigenvalues on hi crystalline x tensor over k, or hi L x. So for each I, all I, well, let's say, yeah, for all eigenvalues, this tensor with q over ql are algebraic integers. With absolute value q to the I over 2. Okay, so this is what we have. So there's kind of this back and forth between the eigenvalues, the statements about the roots of the zeta function, and the eigenvalues of the cohomology. Okay, I'm gonna stop again, and then I'm going to continue with the next part.